In this module, we're going to talk about Stoke's theorem. We're going to introduce Stoke's theorem, discuss it, and use it in one sort of simple example before we look at more complicated examples in the modules after this. So Stoke's theorem is one of the major theorems in vector calculus. We already dealt with a few others. The big three, we talked about Green's theorem. We're now going to talk about Stoke's theorem. The last one we'll deal with is divergence theorem, and that captures vector calculus. Now, I've kind of pre-populated the board here with two things just for some efficiency, but I want to review something we've already talked about and connect it to what we're going to talk about, which is Stoke's theorem. So let's remind ourselves of Green's theorem. It's been a little while since we talked about Green's theorem because we did double integration, which was a whole thing, then we had Green's theorem, and then we did a bunch of examples on double integration and other coordinate systems, and so we've been doing other things for a little while. Let's remind ourselves of what Green's theorem, which is sometimes called, and today this will make more sense, Green's theorem in the plane. So this is the statement of Green's theorem, simply put, that you see in the textbook. And as we talked about in class, this is a simplification of a more general way to say it. But what you normally see is the statement of Green's theorem is that the integral of some function p of x and y dx plus some function q x and y dy taken around a closed contour. Okay? And this is a funny construction, but we'll make sense of it in a minute. So this integrand taken around this closed contour actually equals the double integral of these partials. So you take the partial derivative of the y part with respect to x minus the partial derivative of the x part with respect to y. This is now just a scalar field. And that function, you integrate it, you do a double integral of it over the region R, which is bounded by C. Okay? So that was interesting, right? It relates this line integral to a corresponding double integral. Now, as soon as we showed this, I don't love this form because it's a little easier. This is a funny construct on the left-hand side. This would show up if we had a vector field who had an x component p and a y component q. And you said, well, hey, what's the integral of f dot dr around the closed contour? That makes more sense. There are examples, I keep mentioning work. If f is an actual force, then this integral of f dot dr around the circle would be the work done by the force around the circle. That's cool. There are other examples, but that's a reasonable one. Right? Now, further is we said, well, if this is the vector field f, then this whole thing is f dot dr. But what is this thing? And we showed before that if you actually take the curl of f, even though it has only two components, there's a zero z component to f, because this is in the plane. This is just a 2D situation. If you take the curl of f, you find that is equal to there's a 0x component of the curl and 0y component of the curl because f has only x and y components. So if you write the whole determinant out, you find the curl of f is just the partial of q with respect to x minus partial p with respect to y times the k unit vector. Okay, so it's the curl of f has only a z component. And that's nothing special about f. This is for a general f, right? F is we'll talk about conservative in a minute, right? So that's f. So you can, with these two observations, you recast this as the closed contour integral of f dot dr, so it could be the work done by a force f around this closed contour. This thing is actually equal to the double integral of the z component of the curl of f over the region R contained by C. Okay? So it's the same statement as this, as long as you make the realization that f equals pi plus qj. And it's same statement, just written in a more complicated way. This is how I talked about it in class more, for one reason, and that reason is going to make sense today, because this makes the connection between Green's theorem and Stoke's theorem, which we're going to see. Okay? I'll just, not to beat this to total death, does f need to be conservative for Green's theorem to be true? No, not at all, right? Not at all. If f is conservative, Green's theorem becomes kind of trivial. Because remember, if f is conservative, it means that the curl of f is 0. Moreover, it means that the integral of f dot dr around any closed contour would be 0. So if f is conservative, you have 0 equals 0. So it's true. Green's theorem is true, even if f is conservative, but it's a trivial case. Green's theorem was more general than that. Okay, we've done all this. Now, so the new thing today is Stoke's theorem. And based on how I've drawn this, it's like, well, Stoke's theorem is just a 3D generalization of Green's theorem. Okay? It's almost the same. So Stoke's theorem says we have a three-dimensional region now, right? So we have curves and surfaces in 3D. They're not simple planes, they're general, right? And so we have some surface S that is bounded by some curve C. Okay? So for the same curve C, you could have lots of surfaces bounding it, right? If C was just a circle, you could have a flat surface over that circle, or you could have a big bubble that bulges out. As long as its ends are clamped by the contour C, this is applying. Okay? So we have some surface bounded by curve C. We're going to traverse the curve C in a certain direction, right? Just like we did over in Green's theorem. Right? And we're going to, but now what's positive and what's negative is curious. So we're going to define a convention whereby if you say, kind of a right-hand rule thing, if you curl your fingers around the curve C in the direction you're traversing it, then your thumb points in the positive direction. That's how we're going to define positive. And so we're going to concern ourselves with flux through a positive flux through the surface F's. So if curl is this way, this is positive flux, this is negative flux. Okay. Now, I'm getting a little ahead of us right now. So right now, I just have a surface bounded by the contour C. So now, in addition to this surface and contour, separate from it, there is a vector field. So this vector field is some, who knows, flow field or electric field over the entire universe. It's everywhere. It's got some vector direction pre-existing. And we are plopping this contour and the surface on top of the vector field. Okay, they're independent functions. But we're going to ask, well, what's the integral of things related to F over this contour and over this surface? And we're going to find the relationship between the two. So F is generally a three-component vector field, Pi plus Qj plus Rk, where P and Q and R are functions of x, y, z. Yeah? This is a vector field within the region. So the statement of Stoke's theorem, and I'm skipping all the sometimes very important things like P and Q and R have to be differentiable and they have to be non-singular over the region. They can't divide by zeros. They have to be defined over the region. They have to be well-behaved. So well-behaved is a word we just say sometimes to capture a lot of important stuff. And we'll deal with these important extra features as they come up. But right now, C is normal, S is behaved, F is this, it's got no crazy behavior. Okay. Given all that, this is Stoke's theorem. That the integral of f dot dr on a closed contour C, exactly the same statement as Green's theorem, okay? But now C is a general 3D closed surface, closed contour. That is equal to the flux of the curl of F through the surface bounded by C. And so this is why we did surface integration, then flux integration, because we need it for Stoke's theorem. Because Stoke's theorem is talking about not the flux of F, but the flux of the curl of F. So you have F, curl of F gives you another vector field. That vector field can have a flux through S, right? So you take this new vector field, curl of F, you dot it onto the normal vector like we did for any flux integral, and then you integrate the remaining thing over the surface. But now the surface is bounded by C, and importantly, it's any surface bounded by C. It's almost miraculous that this contour integral of f dot dr is equal to the flux of the curl of F through any surface you could possibly draw that's clamped and bounded by C. Okay. That's Stoke's theorem. Starts to feel pretty crazy, right? I mean, Green's theorem in its own felt kind of surprising. Stoke's theorem should be surprising. Okay. Now, so the steps of computing this, right, it's just now one more step on top of flux integration. So if we're actually doing this in a problem, and the problem says calculate, usually the problems say use Stoke's theorem to calculate this, because this is what's hard, right? Think of this: you get some crazy curve here closed. You remember how hard it is, or challenging it was sometimes to parameterize simple curves just in the 2D plane. Now you got a 3D curve. This is usually the hard thing. And so it'll say calculate this using Stoke's theorem. So that means, oh, okay, I know how to do this. You identify f, and then what are the steps? Once we have f from this, so given it, then I calculate the curl of f. Then I calculate the normal vector based on the surface equation. I normalize the normal vector, so it's unit 1. Then I calculate the dot product between the curl of f and the normal vector. Now I have a scalar field. So I have a scalar field S. Then I decide what surface I'm going to think of as S over some region R, right? You convert the ds to dA using the square root of 1 plus 2 partial derivatives squared. Then you have a double integral. Then you decide which of the two coordinates, and it depends what coordinate system we're using, to do what order to do the iterated double integral in. Sometimes it's easy, sometimes it's harder. Okay, set it up and compute. So it's all the steps we've done. We have just one new one today, beyond the realization of Stokes' theorem. The new one is, well, now we've got to calculate the curl of f. So let's do a simple first example of this. And the first example is, it's not meant to be a difficult calculation. It's just a demonstration of Stokes' theorem as we would use it. As we've said with all these things, a very viable, though maybe sometimes difficult exam question would be verify Stokes' theorem, where you have to do it both ways. You do the contour integral and the right-hand side surface flux integral and show they're the same. That would be an example of the kind of problem you could have. Okay, so here's our example. So we'll say something like this: evaluate. Okay. This. And then just think, what do we need to have? The problem's got to tell you f, and the problem's got to tell you c, right? So we're going to have f, and f's given to us as, f is here, I've got, just some crazy simple f, zi plus x j plus y k. Okay, vector field, it's possible, simple, but possible. And we also got to have c. And c is the trace of the cylinder x squared plus y squared equals 1 in the plane of y plus z equals 2. Okay. C should be counterclockwise viewed from above. So that's also true about C. We can't just actually say C, we really should say the direction of C. So, how do we proceed here? Okay, I'll come back and erase this after. But the first thing, right, is you gotta sketch it. You have to. So we're gonna sketch C. F is a vector field over the whole space. That's fine. Okay, but we're going to draw C first. So let's draw C. Because C is going to also give us the direction on the surface S. Okay. So I've got a trace of a cylinder. So I've got a vertical cylinder. So I've got x squared plus y squared equals 1 in the plane. Right? We know we're doing with 3D. So if x squared plus y squared equals 1, this is a cylinder in the vertical direction. This is a 2D problem, it'd be a circle. But in a 3D problem, we think of it as a cylinder. So I've got this cylinder, okay, of radius 1. It's in the vertical direction. Okay. I'm not finishing it up here because I'm going to draw something. And then we have a plane, okay? A plane y plus z equals 2. So this means here just that z equals 2 minus y. Okay? So when y equals 0, z is 2. When y equals 1, z is 1. When y equals minus 1, z is 3. Right? So it's a plane that cuts our cylinder. So the cylinder would continue to go up. I've got this plane cutting down. This is z equals 1. This is z equals 3. Here we have z equals 2. And this circle is radius 1. So this is the contour. Okay? This sloped, it's not a circle, right? It's not a circle. The cylinder's got a cross section of a circle, but we're cutting through it. Right? So we want to calculate f dot dr. That's what we're actually doing. This is the vector field. I want to calculate the dot product of f around this closed contour. Looks like a hard contour. We just learned Stokes' theorem, so we're going to use Stokes' theorem. Some of the problems will say use Stokes' theorem to blah. But also we could have a problem on the exam where it just says find this. And you have to kind of recognize that the only practical way to do this is Stokes' theorem. I'm going to use Stokes' theorem, and then away you go. Now, once we do Stokes' theorem, the next question immediately is, well, what s? Because I said Stokes' theorem true for any s. Now, when you have a simple curve like this, you want to choose s to just be in the plane of the curve. So we're going to choose s to be what I've shaded. I already jumped ahead. This is s. Okay? Okay? And then it's going to be, you can see s is casting a shadow over region R down the xy plane. So you can't see what we're going to do here pretty soon. Okay? Okay. Now right away, we are going to need a normal vector to s. Right? So the normal vector to s, we're going to calculate it, but this is, the normal vector to s will be like pointing in this direction, right? Why is it up and not down? Because I've defined positive to be my right-hand rule around the curve f, so my thumb points in the positive direction, so this is the positive normal vector n. So now I need the curl of f. Well, what I'm going to do, right, we're going to say, just go through the total motion here. So this c plus f dot dr is going to be, s, the curl of f dotted onto the normal vector s. Okay, got it. So we need the curl of f, we need n, and then we'll build the flux integral. Okay, so curl of f, I'll do that. Curl of f is I, j, k, di x, di y, di z. Okay, and then I have the three components of f. So f was zi, xj, yk. Okay, so this thing, now I'll do the partials as we go here. This one's simple enough, and I often advise to do this in one more step, but I'll take, so I go I, and then I take the remaining determinant, so di by di y of y, which is 1, minus di by di z of x, which is 0. Then I go minus j, and I take this, di by di x of y is 0, minus di by di z of z is 1. Then I go plus k. Okay, now I get this determinant, di by di x of x is 1, minus 0. So this thing equals I plus j plus k. Does that make sense given the surface? That's a trick question. This has nothing to do with the surface. There's no sensibility to ask whether this makes sense with the surface. F is completely independent of the surface. So the curl of F is completely independent. This has no relation. The reason I mention it is because it's actually, the surface is sufficiently simple. You almost think they would. But this, you don't look at this and go, yeah, does that make sense given this? No, it has nothing to do with that. Right? The next part will, right? So this is the curl of F. What else do I need? Well, I need n. So this is the thing I'm calculating the flux of. I got to get it through this normal vector. Okay. So to get n, right, we need the equation for the surface. So the surface, right, is given by this thing. Y plus z equals 2. Okay. It has boundaries, but that's the surface function. So we'll write that as y plus z minus 2 equals 0. Okay. That defines that surface. Now I need the gradient of that. Okay, so di by di x, it's 0i, plus di by di y, which is 1, then di by di z, which is 1, times a unit vector. So this is just j plus k. Does this make sense? Yeah, now you can ask the question. Is this vector perpendicular to that surface? Well, it's only got j, so y and z components, like n does. So yeah, it points at an angle in the positive y, positive z direction, out here. I probably should have drawn this curve more to 45, because this describes sort of a 45-degree angle. But this does make sense. I don't have the normal vector yet, right? Normal vector would be the gradient of that guy divided by the magnitude of the gradient of that guy. Right? So this becomes j plus k divided by the square root of 1 squared plus 1 squared. So this becomes 1 over root 2 j plus k. Okay? That's the normal vector. Okay, cool. So now we need the dot product of those two things. So what I'll do is I'll go into the integral now. Well, here, let's just do this. So the curl of f dotted onto the unit vector. It's fine to do this, but then go into the integral, right? Is I plus j plus k dot 1 over square root 2 j plus k. Okay, so that becomes the dot product. So you take the x components times each other. There's no x component here, so that's 0. And then you have 1 over square root 2, 1 times 1, plus 1 over square root 2, 1 times 1. So that's square root 2. That's the dot product of the curl of f and the normal vector n. Okay, so what we're really doing then is doing a surface integral of square root 2 times ds. So this is now a surface area integral. We don't offhand know the area of the tilted cross section between a circle and a cylinder. There probably is an equation for it, but we're going to pretend we don't know it and we're just going to integrate it out. So I'm going to go over here, just erase this side. So really, what we're asked to find is just square root 2 times ds, right? Because I've calculated the curl of f dot n, this whole thing is square root 2. This is an easy problem. Okay, so then the thing is, how do we do this? Well, don't forget, right? So it's a surface, this is actually a surface area integral, but still, we have to decide, this thing's going to cast a shadow. So either going to integrate over the xy plane, or we're going to integrate over the xz plane. Okay? I'm going to integrate over the xy plane. So to integrate over the xy plane, I need the surface height function, right? And I'm going to use that. So ds will be square root of 1 plus, okay? I need the partial of the surface height, which is z, and I erased my z, but z was, yeah, we had, what was it? Z equals, yeah. So we had y plus z equals 2, so z equals 2 minus y. That was the height function above this xy plane. Okay? It doesn't depend on x, but does depend on y. So I need the partial, so I'm taking the partial of that height function, di z by di x, which is 0 squared, plus di z by di y, which is minus 1 squared. So this becomes, oops, ds is this whole thing times dA. Okay? So this thing will become square root 2 dx dy. Okay? 1 plus 1 square root 2, and dA becomes dx dy because I'm integrating over this region in the xy plane. Okay. Now, so therefore, if this is just I, so I equals square root 2 times, well, I'll leave this as dA for a second. So this becomes a 2 times the area of R. Okay. Well, the area of R we do know, right? The area of R, that's a circle of radius 1. So this becomes 2 times, well, the area of a circle radius 1 is pi times 1 squared. So this whole thing becomes 2 pi. That's our final answer. So this integral becomes 2 pi. Doesn't have any sensible engineering units associated with it, but that's okay. We're just doing our calculus exercise at this point. Okay, so you can see most everything we've done in the course in this problem, from curl calculations to normal vector calculations, right, using the gradient operator, we have the dot product, we have double integration, we have surface integration, we have flux integration, we're using that to do a contour integration. This is the whole thing, all souped up together. Okay, our final answer is pretty simple. Often this is the case, right? When we do these ones, we have a difficult one, and then you use a theorem to calculate something easier, right, to obtain our final answer. So that's Stokes' theorem. We'll look at Stokes' theorem can also be complicated. You can have hard problems. This was kind of an easy one. Okay. So after this, we'll record a module or so about maybe a harder example of this before we move on to triple integration and divergence theorem.